All right, I'll go ahead and get started with the webinar. Thank you to everyone who's joining us today. This webinar topic is field data collection for open pit slope design, and it correlates with the GCE's Fundamentals of Open Pit Slope Design course, for which we have many of our presenters today on the panel. It is an Ask the Experts webinar, which means it is interactive. So we have a panel of experts from the Open Pit Slope Design course who are here ready and willing to take your questions today and discuss the topics related to field data collection for open pit slope design. This webinar is going to run for 1 hour from 9 to 10 a.m. And it is brought to you by the Geotechnical Center of Excellence at the University of Arizona. We are an industry-funded and member-led interdisciplinary center. We focus on collaborative geotechnical research and education with the goal of bridging gaps within and between academia, industry, and fields of study. If you'd like to know more about the GCE, we'd be happy to chat more. Just send us an email at gce@arizona.edu. And as I mentioned, the topic in this webinar corresponds with Section 2 of our newest online professional development course, which is Fundamentals of Open Pit Slope Design. Section 2 focuses on field data collection, and that's what we'll be talking about today. If you are interested in learning more about this course, it is still open for registration. You can use the QR code here, or you can visit our website. And I'd like to thank all of our member companies for their support in putting together courses such as the Fundamentals of Open Pit Slope Design course, for supporting webinars like the one you are in today, and for funding all of our many projects, educational and research both. So thank you to all of our GCE members. We appreciate you very much. And also, I'd like to acknowledge the Large Open Pit Project, who underwrote the course and also produced the textbook, which for which much of the course is based upon, which is the Guidelines for Open Pit Slope Design. And that is currently being updated from the 2009 version with a new version that will be coming out in the near future. So now I would like to introduce who's here today with me. From the GCR webinar team, myself, I'm Jillian Noonan, Senior R&D Engineer with the GCE, and I'll be your moderator today. Also helping me out, I have Allison Brucey, who is our Program Coordinator. Good morning, Allison.
Morning, Jillian. Good morning, everybody. Thank you for being here.
And Christian Ortman, who is a Computing Sciences Researcher with the GCE, will be helping to field your questions today. Christian, thanks for being here.
Good morning, everyone, and thanks for joining us.
And we have Cheryl Bukowski, who is new to the GCE. She is our new Professional Development Program Lead, and this is her first webinar. We're so happy to have her join the GCE team and happy to have her here with us today. Thanks, Cheryl.
Good morning, everyone. Thanks for being here.
And now it is my honor to introduce our expert panel, who are here to answer all of your questions related to field data collection for open pit slope design. So I'll go through and I'll mention each person, and then I'll mention also their contribution to the Fundamentals of Open Pit Slope Design course. But of course, I am sure their expertise goes way beyond whatever module they did present. So we're very happy to have a great team of experts here today, starting with Karen Moffett. And Karen is president for Equilibrium Mining. And Karen also serves as one of our course lead technical advisors. So she's worked to help oversee the development of all of the content of the course and has played a key role in that way. So thank you so much, Karen, for being on our panel today.
Thanks, Julianne. Hi, everyone.
Also joining us is Marisol Valerio. Marisol is Principal Rock Mechanics Engineer with WSP, and she presented in the course a module on core drilling and logging. Thank you so much, Marisol, for being here.
Thanks, Jillian. Hi, everyone.
Next up, we have James McNabb, who is Senior R&D Engineer with the GCE. And James presented a module on surface mapping for structural data. Hi, James.
Hello, Jillian. Good morning, everybody.
Jeff Beal is joining us. Jeff is Global Technical Advisor with Pateau Associates. And Jeff, of course, presented a module on hydrology data collection. Hi, Jeff. How are you?
Good, Jill. How are you? Hi, everybody. Hope you can hear me. Can you hear me all right?
Yes, we can.
Good,
Good to see you.
good.
Thanks for joining.
Yeah, sorry about the
No
delay.
problem. I knew I can count on you.
All right.
And also presenting on hydrology data collection, we have Thomas Fian, who is principal hydrogeologist with Pateau Associates. Thanks, Tom, for joining us.
Yeah, no worries, Julian. Thanks for having us, and hello, everyone.
Next on our panel, we have Carl Lawrence. Carl is Chief Technical Officer with Equilibrium Mining, and Carl contributed a module on the application of machine learning in data collection for open pit slope design. Thanks, Carl, for being on our panel today.
Thanks, Julian. Welcome, everyone.
And we have Dean Riley. Dean is Director for the Mine Hyperspectral Research Consortium with the University of Arizona.
Good morning,
And of
Julian.
course,
Thank you.
Yep.
Good morning, everybody.
Thanks so much, Dean, for joining us. So any questions on hyperspectral imaging, Dean will be well equipped to answer those for our participants today. And we have John Danielson. John is a geological engineer and rock mechanics specialist with BGC Engineering. And John presented in the course a module on automated core logging. Thanks, John, for joining our panel today.
Thanks, Julian. Good morning, everybody.
All right, so that is our panel. And now I will just quickly discuss before we get into questions how you, the participants, can participate today and interact with our panel to ask questions. So firstly, this is a webinar, so you are muted and your video is off. But if you have a question, you can enter it at any time throughout this session into the Q&A, which is a button that's located on your Zoom control panel. So if you click on that button, it should open up and you'll be able to type in a question. You'll be able to see questions that others have typed. If you see a question that you particularly like, you can upvote it with a thumbs up, and we'll make sure to order those questions preference of those that are highly rated. Your questions can be entered anonymously by selecting a checkbox. And we are recording this webinar, so it can be watched later either via the course site or on the GC's YouTube page. And I will note that this webinar is intended for educational purposes only. If you have any specific site concerns, we do encourage you to verify any information before acting on it and to, of course, consult directly with a qualified professional. And thank you for joining us. With that, I think we are ready to get started if my panel is ready. All right, I will pull up first a pre-submitted question that came in through the GCE's course site. And I will welcome all of our participants at this time to enter any questions you might have into the Q&A. So our first question, I'm going to first direct at Marisol, and then we'll also open up to the panel for discussion. So Marisol, if you'd like to start with this question, how do you tell mechanical breaks from natural joints in core logging?
Thanks, Julian. Yeah, this is a really good question, really important to be able to distinguish mechanical breaks from natural joints. And that could be, it could be a little bit tricky, but there are some signs that you can look for that are fairly typical. Mechanical breaks will typically be characterized by clean surfaces that are fresh, free of alteration, usually irregular, rough, and just don't look like they've been around for a very long time. They look very fresh. Very often they're oriented close to 90 degrees to the core axis. So you can tell them apart from natural fractures that way. And usually they're very easy to join with just the hairline separation. If you put the two sides of the fracture and you join them, sometimes it's really hard to even see that there's a separation there because they just fit together so well. On the other hand, when you have a natural break, then you would be looking for the opposite. You have surfaces that look more altered, more weathered. They might have a coating on them. They can be oriented at any angle with respect to the core axis. And if you try to put the two together, they usually don't fit perfectly like a mechanical break would. So those are some good signs to look for.
Thanks, Marisol. Are there any other additional comments from anyone on the panel? I'd invite you to unmute.
Yeah, I'd just like to add, definitely agree with everything Marisol said. And additionally, hopefully you're able to talk with your drillers. I know that's not always the case. Sometimes you're logging at a core facility that's nowhere near the drill rig, but ideally you can communicate with them. Oftentimes drillers will actually mark with like a wax pen their mechanical fractures. They don't. Sometimes they're breaking the core to put it in a box or handling it rough. So they actually do see a lot of mechanical fractures occur at the time. And so they're able to mark those. So hopefully they're doing that. Also, when you're logging, sometimes it's a good idea to have a way to flag certain measurements if you're not sure. So if you're measuring a structure and you're like, I'm not really sure if this is a mechanical or natural fracture, maybe you can just tag that one as possibly mechanical. So then when you throw it into your stereo net, you're able to filter those out if it looks erroneous. So, anyways, just a little addition there.
And maybe one more nuance. I also agree with everything Marisol and James brought up. But mechanical breaks can occur at any angle. And natural discons can also form at 90 degrees to the core axis. So like Marisol was saying, these are signs of things to look for to differentiate. But it's good to look at the discon holistically.
And when in
Another
doubt too, it's always good to go back and look at, the photos in the split tubes or ATV imagery just to get an idea of whether not on specific fractures, but just overall, are we overestimating the amount of natural fractures?
Yeah, I was just going to add to tie it to some of the future trends and things that we see, and I'm sure John can comment on this as well. But this is one of the most challenging things too when dealing with machine learning and automated logging is like, how can you tell the difference between mechanical breaks and natural joints? It's just as hard for machine to tell that as it is for a human. So it doesn't get much better, and it's one of the bigger challenges from the machine learning side of things.
And someone has noted in the chat, and if the mechanical fracture is in a vein, are there any additional considerations for in a vein?
Yeah, I think with veined core, it's possible, it's more frequent to see mechanical breaks occurring along veins. If you have a lot of them, they're a plane of weakness where the fractures can occur. So again, something to look out for. Similar signs with a vein. You can also, get, like James was saying, get the information from the driller. Sometimes look for signs of drilling induced mechanical breaks, like you can have scuff marks and things like that. That would help to indicate that. But yeah, certainly with vein deposits or any type of core that has pre-existing planes of weakness, it's more typical for mechanical breaks to occur along those during handling and drilling.
Yeah, that's a good point. You get into almost a philosophical debate of if you've got a mechanical fracture that breaks along an existing weakness, would that possibly be an open fracture after you've blasted and mined the rock so that it actually could be a geotechnically significant feature? So it gets a little tricky there.
All right, thank you, panel. We do have another question that came in also on the topic of core logging. So while we're on this topic, I'll bring that up. Again, this is directed towards Marisol, but we'll also open up to the panel for discussion. So you talked about good documentation, good pictures. If you are not logging on site and there are no marks from the drillers, what is the best way to identify material that should and should not be included in the total measurement? So Marisol, would you like to start with this?
Sure. Yeah, that's also a really good question. And I think this is referring to instances where you have redrill or sloughing of the hole where you get material that's out of place. Perhaps that's what this is referring to. Most of the time it can be, if you're dealing with strong rock, it can be fairly easy to tell that material because it just looks out of place. It often occurs either at the beginning or at the end of a run. So you would be looking at, the drilling blocks. If you see material that looks like it's a lot weaker than the rest of the rock, seems like it's out of place, it likely is and should be marked as potential redrill and not included in the RQD or the TCR measurements and the other measurements. But yes, certainly the ideal situation is you are logging at the drill rig and are able to communicate with the drillers. When that's not possible and you are looking after the fact, then those are signs that you can look for. And sometimes, yeah, you would, especially in strong rock, you would expect to have a total core recovery that's close to 100%. If you now see that you have a lot more core, that's another sign, or big discrepancies in the total core recovery between one run and the other that aren't exactly clear where they came from. That's something else that can be used.
All right, thanks, Marisol. Any other comments on this from the panel?
I guess just to piggyback off what Marisol said, if you, in an ideal case, if you have something like TeleViewer and you're matching fractures that you can see or just features that you can see in the TeleViewer with the actual core, and you start to see length discrepancies there, you might suspect that you've got some sloughed material as well. That's kind of an ideal situation, though.
One of the things to think about also is having an understanding of the lithology that you're drilling through so that you can identify lithologies that do not match within those sections. So that's of importance to understand going in that the lithologies in their natural sequence, because that'll lead you to be able to identify materials that don't fit within it as well.
Thanks, Dean. We do have a couple of live questions coming in, and I think that's a good lead into one of them here is how do we differentiate between a weathered and an altered natural joint in the core log?
I could get us started on that one, Jillian. So there are two main ways that I can think of as a starting point. Weathering typically occurs closer to the beginning of the hole, versus alteration can occur anywhere in the hole. That's one thing you might consider when you're close to the beginning of the hole. A lot of what you see might be weathering. Coloring is another way, and alteration. It's important to know and keep in mind that alteration can both contribute to weakening the core or strengthening the core depending on the type of alteration. So I think really good practice is to have a good conversation with the geologists on site that are familiar with the rocks that you're going to be encountering, and having ahead of time an idea of where you're likely to encounter weathered zones and where you're likely to encounter alteration and different types of alteration and different degrees of alteration, and so that when you're drilling, there's already ideally a cross-section through the model and the types of alteration that you're expecting to encounter, and then you can cross-check that based on what you're seeing come out of the ground. So that's just a couple of thoughts there.
Any other thoughts from the panel? Although Marisol covered it well.
Oxidation is what I always look for. This is Jeff. So oxidation is what often gives it away. So often that's a key thing that particularly we look for with water. So
in addition to what Marisol and Jeff mentioned, is you can also, if you have access to handheld spectrometers, you can use something like a PIMA or an ASD or SpectroEvolution. They'll have different mineralogy that can be identified with that you can place directly on that mineral in the core at the point. So that's one piece beyond the visual recognition that has a much more definitive way to derive the mineralogy for it, in addition to the core imaging systems that are out as well.
I'll just add, Marisol made a really good point that when you're logging, you should have some idea of the geologic context. You shouldn't be logging blind. It's always good to know what you might be expecting in the core.
All right, we've opened a good discussion here with some more live questions coming in based on the current discussion. So I'm going to pull up another on, let's see, identifying faults So how would you identify faults in highly fractured rocks where every structure looks like faults? And then someone else from our participant group commented on that. By fault, do you mean shear planes? So I will open this up to the panel.
I guess I can get it started. Certainly offset, depends. I don't know if this is specific to core, this question or not, but it might be hard to see offset in core. But generally, if you're out in the field, look for offset features to distinguish faults from highly fractured rock, or other things like Rydell shears. Again, these are pretty challenging to see in core, but in core, you could look for things like slicken sides, other indicators of kinematic indicators of shear.
Thanks, James. All right, another one from our live group here. Should you log a healed fracture as a discontinuity? Marisol, would you like to go?
Yeah, I can start us on this one. So healed fractures, I would say it depends on the context. Generally, no. Healed fractures are considered closed fractures, and so in most cases you would consider that not as a discontinuity. However, there may be cases where you have a lot of healed fractures, such as veins, for example, vein deposits, where you might want to keep track of that, especially if you're designing, for example, bench scale design where you expect a lot of those healed fractures would open up with blasting. So you may want to consider that when analyzing the data and developing the design. So I would say if you're in an environment where you're going to be seeing a lot of them, it might be a good idea ahead of time to come up with a way to log them as closed fractures, and then you can factor that into how you want to analyze them for design purposes after.
Thanks, Marisol.
Maybe one thing I'll add is again, certainly agree with all that. I have seen folks miss discontinuities that are infilled by like a stiff clay if it's thin. To make sure you're not doing that, it's good to like run your hands along the core and give it a little finger pressure to make sure you're not missing any of those types of discontinuities.
That's a really good point, John. Sometimes you might even have like a little brush clean off the core a little bit. Sometimes it's quite dirty, covered in drilling mud.
All right, while we have John, I'm going to pull up a pre-submitted question related to automated core logging. So John, this question was asked via the course. What are some current challenges that are still faced when using automated logging methods with core photos?
Yeah, Carl actually brought up one of the biggest ones, which is differentiating between mechanical and natural breaks. It's something humans struggle with, and evidenced by the question we received earlier. Some folks deal with this differently. Like some people say, well, if it's a break, there may have been a plane of weakness there already. Other folks have tried to feed enough examples of natural and mechanical breaks into their models to sort of classify each of these as natural mechanical with varying success. The tricky part here is because humans are not perfect at it, the training data we're feeding these models is not perfect, and so the models have imperfect performance as a result. Jeff Owen gave a talk at Slope Stability 2024. Jeff Owen from Tech, who's done a lot of great work on this stuff. So they had success by getting an experienced logger, locking him in a room for 3 months to come up with a trustworthy mechanical and natural data set, and noted some good performance, but it's certainly something people still struggle with. Other aspects of automated logging with core photos is if you're just doing it from photos, you don't know the strength of the material, and that means and you know even less about the strength of material along discontinuities and infilling discontinuities, which means there will be uncertainties when you're estimating RQD because RQD, the core has to be sound, generally like greater than R1. You don't know that just from the photo. And without strength, you can't accurately estimate joint condition because joint condition depends on the strength of the wall rock. So yeah, automated logging from core photos. Well, I think it's incredible. It does have some gaps that folks are trying to address in different ways.
Thanks, John.
Other little things that I've seen in the tools that sort of in the attempts that we've made at it is just simple things like the marking on the core is helpful sometimes for identifying the breaks, but it's recognized as fractures sometimes because we're just writing markings everywhere, so it's difficult to differentiate the text. Other things, just the quality of the image or how the core is being stored. Every time we start working on it, it's like, oh, our core images are great. And then we realize, okay, sometimes they're in like wooden boxes, sometimes they're in cardboard boxes. So it's the quality of the images isn't quite always the same. And that's difficult when we're crossing different sites and dealing with core images that are quite old. So the quality of the inputs certainly has a large impact. Definitely it's improving now when we're moving away from photos, moving more into 3D scanning technologies. That's sort of a much better quality of data that we'd be dealing with for the training.
All right, thanks for that input, Carl. Couple
What's
more
the key
questions.
there then with the quality? Is it just making sure that consistent photos are taken?
I think that was for Carl.
Yeah, Carl
Yeah.
or John?
Yeah, I mean, I think one is consistency, and I think this is, generally in our industry, it's like collecting things consistently, making sure you have that same thing. But at the end of the day, it's still a 2D static image, right? I think there's more potential in the future with the scanning technologies because there's only a certain amount of data you can extract from the 2D image. You can't see the 3D core. One of the questions that we're getting, for example, is can we get the fracture roughness? Can we get the orientation? And you can to a limited extent, but it's still a 2D image, and we're trying to extract 3D information from it.
To add in the illumination when you capture 2D images. So if you change your angles, your illumination changes. So even just slight adjustments with the hand or whoever's taking it makes it a challenge on being consistent with core photos unless you have a rig that has fixed illumination on the one side and then you have your camera set up directly overhead to mitigate some of that. But you have to have an established consistency for your core photos. And doing it manually is a challenge. And that's where Carl's right. With the automated and the line scanning capabilities are a much more consistent way to produce reproducible data.
I think the other thing to think about is, the true value of this is if we could automate it across all sites. So if we do it for one site, we basically need to make it reproducible across all sites. So we need everybody using the same camera and everybody using the same setup. And that's, giving historical photos is one thing, but it's not something that we have right now until we get into something that's a bit more standardized in the industry.
Yeah, maybe there's one more thing there. We can only rely on technology for so much. Computer vision tech is getting more robust to different lighting conditions. It obviously still makes a huge difference, and a lot of the automated photo methods still rely on like a lot of pre-processing and making sure things are standard. I'm hopeful that things will continue to improve, and folks will have to spend less time on pre-processing images.
So one other thing on the challenges, particularly on photos that we've experienced, is picking out things like mechanical or like fractures or breaks. It's relatively easy. I think most people have done it, and it does it at a pretty high success rate. The thing that becomes a bit more challenging is picking out textures, vugginess, or just, stuff that aren't just clearly apparent in photos that are challenging to people. So I've seen some of the machine learning technologies just struggle with the texture aspect when we're trying to classify veins, things like that. It's because it's basically a coloration on the core, and it's not as successful as like picking out hard breaks.
All right, thank you, panel. I'm going to pull up a couple more live questions that came in on the topic of core logging before we might switch gears just a bit. So firstly, on interval picking, does interval picking have a significant impact on core logging, especially for rock mass classification? And I will invite Marisol, has unmuted, to start.
Yeah, I can start on this one. So interval picking, yes, absolutely is one of the most important steps in core logging, and that it's one of the things that need to be thought out well ahead of time. What's going to be the minimum interval length and the maximum interval length for a project. Very typically, the maximum interval length will be equal to the length of the drill run. So we usually 1.5 meters or 3 meters is what is typically drilled, and the minimum interval length is usually assigned either as a percentage of the total drill run length or as a set number. So that could be, I don't know, if you're looking at 10% of a 3-meter run, it might be a 30-centimeter interval. Apologies for the US people, I'm thinking in metric units here. But yes, it's absolutely very important to have loggers that are trained in how to identify differences that would require selecting interval boundaries. So for example, a significant change in the rock strength or a significant change in the fracture frequency. Always a difference in the rock type would warrant changing assigning a new interval, or significant changes in the degree of weathering or alteration. And that's done so that changes in the rock mass can be visualized and characterized properly, rather than blending several different types and behaviors of rock into a very large interval that then becomes blurred and is not possible to have as much granularity when doing the designs. So those are my initial thoughts on that. Happy to hear what others have to say about it.
Anyone else from the panel like to contribute? If not, I trust that Marisol has done a great job of explaining this question. All right, I'll pull up one more. Thank you, Marisol. And thank you, participants, for all of your great questions that are coming in. We appreciate your participation. All right, so another from the live group on drill core size influences. So if drill core size influences breakage in the core, are there any considerations or factors to ensure representative data is collected regardless of the core size? Or if you'd like to comment on which core size is best for geotechnical drilling. And again, I'll invite anyone in the panel to start. Marisol?
Yeah, I think so. In terms of drill core size, some of the most typical sizes I think that are used, or at least that in my experience I've seen, are usually NQ or HQ. And yes, certainly when you have smaller core sizes, you tend to see more mechanical breaks. So it's something that should be considered. Now, it also depends on the rock type. If they're for weak core, I think larger core sizes are more typical. So what size is best for geotechnical drilling? I would say for a campaign, one of the things I would suggest is to have a consistent drill core size throughout the project, and ideally for campaigns over time, so that you're not introducing differences in the data due to differences in core sizes. And it's definitely something to be considered for lab testing as well. Now, for lab testing, there are empirical corrections that are widely used in the industry to try to take, when you have multiple different core sizes, normalize them to, it's a 50 millimeter diameter, the correction that's mostly done. So that's something that should definitely be kept in mind as well. And I think something that will likely be covered in subsequent webinars after this section.
Even one other,
sorry, John.
one other consideration there is we're getting these like pinhole ideas of the rock. And another reason why I like HQ over NQ is I think in general, it'll give you slightly more representative orientations and idea of roughness, because structures can vary quite a bit from spot to spot, and the bigger size over which you can take a measurement, the more representative it'll be. It's still only a drill hole, but it makes a little bit of a difference.
I'll just add that at least for the your RQD length takes into account the diameter of the core, or it should. So at least that's somewhat normalized to the drilling diameter.
All right, thank you. There are a few other questions relating to core logging RQD that are coming in live. I will invite the panel to, if they wish, to go in and type some answers as well. You have that option to provide a written answer to anyone in the Q&A window. But I'm going to just change gears here for a bit and engage my hydrology data collection experts that are here today. And that is Jeff and Tom. So you guys need to wake up now. We have a question that came in on, let's see, a few questions related to hydrology data collection. The first I'll pull is a pre-submitted question asking about constant discharge tests. Specifically, how long would you want to pump at a constant rate? So I would ask Jeff or Tom to start with this one.
I guess in some regards, you gotta, well, go ahead, Jeff.
Go ahead.
I was just gonna say, in some regards, you gotta think about where you can take that water and where you can put it. You don't want to certainly be recharging it right back to anything that you may be testing, but you know, I mean, it depends on the nature of what you're trying to do, Jeff. I think you know, in some regards we get by with 24 hours, but if we're looking at stuff that's more longer term, you know, 3 days, 7 days, you know, 10 days, those are kind of things that you want to take a look at. But it depends on how much time, money, and real estate you have, I guess.
Yeah, a couple of pointers would be, if you can, let the drawdown stabilize. If you can pump it that long till it stabilizes, that's always a good thing to do, provided it doesn't take that long. And another thing is to pump it long enough so you get a response in monitor wells. It's important, if you're doing pumping tests, that you have monitor wells. So there's a couple of pointers. Try to get the drawdown to stabilize, try to get the pumping rate to stabilize, try to get responses in observation wells. And another thing to consider is recovery. Recovery is really important, not in terms of aquifer parameters, but in terms of looking for storage removal. And if you have a pumping test and it doesn't recover, it's telling you you're in a compartment or a system that doesn't recharge. And that's really important, particularly when looking at dewatering or slope hydrogeology. So a couple of pointers there.
All right, thanks, Jeff and Tom. Any other comments from the panel?
Yeah, I mean, you know, if you're doing early stage tests, that's a good. But I mean, you know, if you got a project and you know you got to dewater it, the longer you can do the tests, the better. And if you're in an active operation, just roll the tests into production if you can. And so, got a couple of situations where we've got a couple of test wells, and I'm saying to the guys, don't look at them as test wells, just get them online, get them going. And, if you got the wrong pump and you need to change it, do that later. But consider them as trials or early wells. And so really, if you got no other constraints and it's not a study, but you're going into operations, pump them as long as you can. But essentially, with any hydrology program, the more water you can get out of the ground, the more you'll understand the hydrogeology.
Yeah, and I would certainly agree with that. I think, in an operating environment or something that's going to become an operating environment, maybe already permitted, that makes complete sense. But in the other regards, if you're looking at obtaining permits or the things, you got to take a look at the regulations and wherever you may be and see how long those tests need to be conducted and what type of information and things the inputs to the model may need or inputs to regulations and local ordinances might need.
Yeah, I mean, that is the regs are a good point. I mean, I was just at a site in Peru last week or the week before last, and they had a couple of wells where they needed to pump them, and they didn't have permits to pump from that sector. So they pumped them and called them tests. But really they were just looking to get some data prior to permit. So they had to treat it pretty carefully. So that's a good point. You got to figure out what you're permitted to do. It's increasingly becoming an issue these days.
All right, thank you very much. I'm going to pull up another live question that came in from our participant group. I'll read it through. It's a little bit long, but I'll open this one up to the entire panel to discuss. So the question is that in the groundwater module in the course, the presenter made note of not accounting for water in your RMR estimation if groundwater is already accounted for in your model, so as to avoid double counting. They would normally lean the other way, looking at RMR as a rating for the rock mass and the piezometric line as a different variable as it relates to water and pore pressure. Is this something that the panel can discuss? So I'll open this up. I see Jeff, you've unmuted. Go right ahead.
It is. Yeah, I can have a talk of that, but I don't know whether it was me that said it. I don't remember saying it, but I think it's very valid not to account for RMR because water is the one thing you can control, and water is the one variable. So I think if you don't, so that's a reason for not including water in the RMR because it'll vary. You can control it. So you're dealing with the rock mass rate and then considers everything else apart from water, and then you consider the water separately. That's typically the way I would look at it. I don't remember saying that in the course. Maybe somebody else said something, but that's the way I would look at it, is to not account it with RMR.
It definitely could have been another presenter. Any other thoughts from the panel for this question? We do have Jeff Beal, so he knows a lot about hydrology. All right, if no more comments
I mean, we've had the conversation at a few different sites, and essentially because you can control and vary water, the consensus, in my experience, is not to include it. Which I think is what the question's saying, or certainly the end of the question is saying.
All right, thank you for that, Jeff. If you have any further questions, whoever submitted this, feel free to type those into the Q&A for further clarification. Keeping with the topic of RMR, this is a question that came through, hold on our course discussion board. And this one is relating to actually Carly Magg's presentation on surface data collection. She is unable to join us today due to the timing of the webinar, but perhaps I'll ask Karen to start with this one and then open up to the panel. Thiago would like to ask about the RMR rating. During the course, one of the presenters said that we should calculate an average value for the rating and not use the exact number in the table. What is your opinion about this? And we were thinking with table, that might be with regards to the Beniowski table.
Yeah, I mean, I think it would be interesting to hear the whole panel's thoughts on this one because I've seen this question be fairly controversial and people get quite excited about how we should be or shouldn't be doing it. And in my opinion, I don't think that there's a hard and fast rule. I personally prefer to use the exact number in the table, like use the rating as it is, and basically pick the rating that best matches what you see in the core. And usually it's a joint condition one that's a bit more subjective, and people like to use averages because it's hard to, with those sort of the less quantifiable metrics, we can get quite indecisive about which bin things fall into and want to use a value in between. But I think sometimes we overthink it, and I just prefer picking the value that best fits what you see for the logging rather than trying to fit things in between. But as I said, I don't think there's a hard and fast rule. Interested to hear what others on the panel think on this question.
I would agree with that, Karen. So one of the reasons is because, most instabilities are controlled by discrete features. So trying to get to average is you can miss things. So I would agree with you.
Yeah, I also generally agree. We do sometimes use continuous functions because if you're just reading the numbers from the table, an ArcED of 76 will have the same score as an ArcED of 89. So sometimes we do map the bins to account for variation within the bin. But yeah, it depends.
Anything else from the panel? Good question from Thiago. Thank you for that. All right, we have about 10 minutes left in the webinar. There are a number of questions still open in the queue. I will also note that there are some typed answers that have been provided that you can find under the Answered tab for those of us that are here in our live group. All right, I'm going to grab a question for Carl. So Carl did a presentation on the application of machine learning in open pit slope design for the course. And this is a short, quick question here, maybe not a quick answer, but a quick read for me. So Carl, can anyone use machine learning?
Short answer is yes, 100%. I mean, I think it comes down to like the types of tools that we use. Everything now is sort of with Google and Facebook and Amazon, they all have their different versions, and most of this stuff is open source. The one stipulation of that is if we're using it internally for our tools, then it's open source. If we start to try to use it in enterprise applications, then you start to have licensing requirements. But yeah, anybody can Google, how to use machine learning with Python, and you'll bring up a suite of different tutorials to be able to learn. And, my advice would be start simple. Don't try to solve, the world of problems. Just start on a very simple data set so you can understand some of the basic features and some of the basic tools, and then do more training. There's various levels of training online that you can get to. Some are basic introductions, and then others are more detailed, and you get more into the theory and the mathematics of it. So it's definitely, we definitely are in a world where information is freely available. So anybody could really pick it up if they have a keen interest to do so.
I'd like to add in with what Carl was saying that, yeah, start simple, and if you're not knowledgeable about the area of where you're applying it, get guidance from your experts on your teams or other people to guide in, because machine learning has a The tendency to crap in is crap out if you have very little knowledge of what you're trying to solve. So that's where your expertise really matters into help leveraging machine learning as a tool. So my opinion would be start simple, like Carl was saying, but engage your experts, or if you're the expert, start simple with knowledge and well-defined problems.
This is certainly not my expertise, but as mentioned, there's a lot of tools out there, and the one that I've used is the MATLAB machine learning on-ramp, which I put in the chat for you. There's, like I said, there's tons out there. I've used this one, and it was great. So that's a good starting point.
And I'm going to follow in with what James is saying. Machine learning is really, and this may be a little heresy to some, just statistics. People, it's an automating statistics. If you go back and look at it, it's really your basic sets of geostatistics, statistical algorithms, and they're all where it stemmed from. It's been recasted because people did not like the framing of statistics, or they are averse to it. So while, but it still goes back into being the expert at what you're wanting to do, knowing simple things, and starting and working the algorithms as you know it. You don't start complicated. If simple works, simple solves it.
I agree with Dean. I think a good example of that is just core logging, right? I can take a geotech engineer and train them to do the machine learning on the core logging, but it's really difficult for me to take a data scientist and train them to do the core logging because they don't have that background. So it's your expertise is really much more difficult to train than it is to train someone to use machine learning, just because that's just a mathematical tool and a package that's generally available today for anybody to use.
Yeah. And maybe one more thing is, and yeah, absolutely anyone can use machine learning. As with any of our tools, as they get more complex, it can be a little more difficult to understand what's going on. And that just means checking the results and making sure they make sense, and using common sense are just like even more important judgments, even more important than it was with simpler methods.
And to what John was and Carl both have said, and add in, because I use this extensively, at least in the world where I've used it, the subject matter expertise integrated with machine learning always outperforms generic machine learning algorithms. And that will probably hold true because, like John was mentioning, your subject matter expertise is paramount in you solving the problem, just as Carl mentioned as well. And Carl's example of training the geotechnical engineer to use machine learning algorithms is spot on. It's much easier that way than training the data scientists. So your expertise truly matters.
Thank you all. You make good points. All right, we have 5 minutes left in the webinar. Any final comments on this, or I can pull up one more question I think we have time for. And I do want to note for our live group, and also one of the pre-submitted questions were with regards to slope performance and slope monitoring that will be covered in a future webinar. Once we reach section 7 of the course, we will be focusing on those topics in detail. Okay, one final question from David. This is a pre-submitted question. Through the Qualtrics survey, how can I integrate field data by developing best practices in rock quality and control methodology in a mineral geochemical study? And I will open this up to our panel. If anyone would like to start, feel free to unmute.
So I'll take a stab at that. I guess it's a little bit of a ambiguous question, but I'll take a stab at it. So, I mean, if you're looking at mineral geochemistry, i.e., ore body geochemistry, then one of the things you look at is alteration. one of the key things is alteration. And the way that relates to different mineral assemblages. And obviously alteration is a key thing for slope design also. So I think there's some pointers there. You know, in the porphyry copper world, there's definitely correlation between mineral geochemistry and rock quality. So I think it's very difficult to get precise correlations, but I think there are some pointers from the mineral geochemistry that you can apply as general guidelines to rock characterization. And, you know, you may want to use that as a basis for sample distributions, but you know, it's not the bottom line, it's a pointer. And so yeah, you've still got to go back and do the basic rock quality testing. That would be my take on it.
Thanks, Jeff. And Dina, I'd seen you had unmuted. Did you have anything that you wanted to add?
I was trying to decipher the whole thing. I think what Jeff was saying is spot on. The other pieces that you could do, if you've got good rock quality and control methodology, it'll translate over into your mineral geochemical study. So if you're collecting everything from fresh to completely weathered rocks, as long as you follow your standard methodological practice and note that for your geochemical study, your chemistry will balance itself out. So I wouldn't let the mineral geochemical study influence what you're collecting for the rock quality and control, because you're documenting and recording across the way. I would just have a completely integrated field book and notes with it.
All right, thanks, Dean. Any final comments from the panel on this question before we close the webinar? All right, well, we had quite a variety of questions today, which was expected considering the broad topic of field data collection for open pit slope design. Our panel has done a great job addressing the questions today. We really appreciate your time and your expertise and for being here with us. Also, thank you to the participants who joined us live today. We did record this webinar, so it will be available for later viewing on the D2L course site as well as on the GC's YouTube. There are some written answers to questions that have been provided, so I will leave the webinar open for just another couple of minutes so that if you haven't had a chance to read those, you can go in and read those. And I will again show you the registration information for the course for which this webinar is based on, which is currently still available for registration. And if you would like more information, feel free to reach out directly. And thank you so much to our panel. We really appreciate you, and everyone, please have a great day. We'll see you at our next webinar, which will focus on the model portion of the open pit slope design. So that should be a really good one coming up. So keep an eye out for that. Thank you so much.